Assalamu alaikum. So we continue our video about pure substance. So we stopped here in last video. So we'll continue. Okay, another example. Temperature of superheated vapor. Determine the temperature of water at state of P. That means pressure is 0.5 megapascal and H 2890 kilojoule by kilogram. Okay, the temperature of water at a specified state is to be determined. Analysis at 0.5 megapascal, the enthalpy of saturated water vapor is Hg is 2748.1. This is at 0.5 megapascal. The enthalpy of saturated water vapor is Hg 2784.1 kilojoule by kilogram. Since H is bigger than Hg as shown in the figure, so here we have the figure here, we have 0.5 megapascal, this is the curve for 0.5 megapascal. We have Hg from the table, and H is bigger than Hg, so we are in this region. That means we are in superheated vapor. We again have superheated vapor at 0.5 megapascal, so the pressure is 0.5 megapascal, and we can use the table of superheated vapor. If we look for the enthalpy given, which is 2890 here, in the table there is no value of 2890, so in this case we have to make interpolation. In the table we have for 0.5 megapascal we have at 200 it's 2855.8, and at 250 is 2961.0. So here we have to make interpolation. That's me. How to make the interpolation? We draw a line. Here it's the t-axis. This is h-axis. I have the 250. I have 2961 enthalpy, and here we have at 200 we have 2855.8 kilojoule by kilogram, and we are looking for the temperature here to get 2890. So this is it's 2890. So we are looking for the temperature for 2890. So what we have to do here, since we have a line, so we have the same slope at each point. So we can write 250 minus 200 divided by 2961 minus 2855.8, which is the slope of the line. It will be equal to 250 minus t divided by 2968 minus 2890. So I repeat, since we have a line here, so we have the same slope at each point, so we can write that the first slope it's 250 minus 200, 250 minus 200 divided by 2961, which is the h for 250, minus the h for 200. It will be equal to 250 minus t divided by the h of 250 minus h of t. So here in this equation we have only one unknown t, so we can calculate t. Okay, so this is what we call interpolation, linear interpolation. Linear interpolation. So using that we can calculate t, and the t is 216.3 degrees C. So it doesn't exist in the table, but we have 250 and 200, and we know that t is between them. So we can make interpolation and find exactly the value of t. Compressed liquid. The compressed liquid properties depends on temperature much more strongly than they do on compression. So compressed liquid is characterized by high pressure. It's a high pressure, characterized by high pressure. P is bigger than P sat at a given temperature. Is the inverse of superheated vapor when it's at low temperature. Lower pressure, lower temperature. Here we have T is smaller than T sat at a given P. Lower specific volume. So we have V is smaller than Vf at a given pressure and temperature. Lower internal energy. U is smaller than Uf at a given pressure and temperature. And lower enthalpy. H is smaller than Hf at a given pressure or temperature. At a given pressure and temperature, a pure substance will exist as a compressed liquid if T smaller than T sat. If you remember, at a given pressure, if T given is T smaller than T sat, we have a compressed liquid. So we are in this region. Okay. Now, compressed liquid, we have Y is it's equivalent to YF at T. That's mean Y it can be the specific volume, it can be internal energy or the enthalpy. So if we are in compressed liquid, we can take V equal to Vf, or we can take U is equal to Uf, or we take H equal to Hf. This is only in compressed liquid. So we can approximate V at Vf, U at Uf, and H at Hf at T given. Okay, so more accurate relation of H, for example, H is Hf at T plus Vf at T, P minus P sat at T. So given P and T, V will be Vf at a given T, U it will be Uf at a given T, and H will be Hf at given T. A compressed liquid may be approximated as a saturated liquid at a given temperature. That's mean if you have the curve like that. So here we have Vf. So all in this region is compressed liquid, and V will be equal approximated by Vf, which is at this point Vf. This is the specific volume for the saturated liquid. So it can be approximated. In this example, we are going to make to show that the approximation can be taken. So approximating a compressed liquid as saturated liquid. Determine the internal energy of compressed liquid water at 80 degrees C. So the temperature 80 degrees C and 5 megapascal. So this is the pressure. So here the temperature and the pressure are given. Using A, data from the compressed liquid table, and B, saturated liquid data, what is the error involved in the second case? The exact approximate value of the internal energy of liquid water are to be determined. So here we have at 80 degrees C, the saturation pressure of water is 47.416 kilopascal. And since 5 megapascal, which is the pressure of the liquid, is bigger than Psat, we have compressed liquid as shown in figure 3. So we are here at 5 megapascal, at 80 degree. So U can be approximated by Uf at 80 degrees C. So we have compressed liquid. So the phase description is compressed liquid. So from the compressed liquid table, which is A7, we have P at 5 megapascal and T 80 degrees C. We get U, the internal energy, 333.82 kilojoule by kilogram. This is from the table. Okay, the value of U for 5 megapascal and 80 degrees C. We have U, this value. From the saturation table, table A4, if we approximate U by UF at 80 degree, we get 334.97 kilojoule by kilogram. This is when we make approximation, the compressed liquid by saturated liquid. So now we can calculate the error between this value and this value. So it will be 334.97 given by the table minus 333 by 0.82 given from the table as saturated liquid, divided by 33.82 multiplied by 100 to get the percentage. So the percentage is 0.31%, that is smaller than 1%. So there is no big error if we make the approximation of compressed liquid by saturated liquid. That means this region is as we are here, so it's approximated by the point here, saturated liquid, so which is less than 1%. So if we make the approximation, there is no big error if we assume that compressed liquid is approximated by the saturated liquid. The ideal gas equation of state, any equation that relates the pressure. So the pressure relationship between pressure, temperature, and specific volume of a substance. This is called the equation of state. The simplest and best known equation of state for substance in the gas phase is the ideal gas equation. So we have ideal gas equation of state. This equation predicts the PVT behavior of a gas quite accurately with some property selected regime. So we have, for example, for the ideal gas, we have P equal to R multiplied by T over V. V here is specific volume. Here P multiplied by the volume is RT, ideal gas equation of state. So this is the ideal gas equation of state. If R is RU over M in kilojoule by kilogram degree Kelvin, or kilopascal meter cube by kilogram degree Kelvin. So R is the gas constant, M is the molar mass, so that means the mass of the molar, so kilogram by kilomole, and Ru is the universal gas constant. So R is Ru over M. Here we have some value of R here, and Ru, some value of Ru. Okay, the ideal gas equation of state, we have P1 V1 divided by T1 is equal to P2 V2 divided by T2. This is the ideal gas equation at two stages for a fixed mass. So when we have a fixed mass and fixed, so we have this relationship between two states. Equation two states for fixed mass. Mass is molar mass multiplied by molar number. M is Mn. So N is the molar number, M is the molar mass. So and M is the mass. Various expression of ideal gas equation. V equal to M multiplied by specific volume. So we can get the equation PV equal to MRT. MR is MNRs. It's equal to NRU. So PV equal to NRUT. This is the second equation of mass. Of ideal gas, and since V, the volume is N multiplied by V bar, so PV bar is equal to RUT. But the most used one is this one, and if we have a fixed mass, we can use this one. Note, the real gases behave as an ideal gas at lower density and low pressure. So if a gas with high temperature, if a gas is has low density, low pressure and high temperature, it can be considered as ideal gas. In water vapor and ideal gas. So at pressure below 10 kilopascal, water vapor can be treated as ideal gas. So we can write, for example, P1 V1 divided by T1 equal P2 V2 or T2. For example, this is the equation of gas, or PV equal MRT. At higher pressure, however, the ideal gas assumption yield unacceptable error, particularly in the vicinity of the critical point and the saturated vapor line. So at a high pressure, the water vapor cannot be considered as ideal gas. In air conditioning application, the water vapor in the air can be treated as an ideal gas. Why? Because we have low pressure. Low pressure. In steam power plant application, the pressure involved are usually very high. So here the pressure is very high. Therefore, ideal gas solution should not be used. In steam power, we have high pressure. High pressure. So in this case, we cannot consider that the steam is ideal gas. The criteria for low pressure and high temperature is relative to its critical temperature or pressure. So this is the curve of T versus V, specific volume, and here we define the region of ideal gas. Okay, so it depends on the temperature and specific volume, and this value are the error made between it's a percentage of error. It's V table minus V ideal divided by V table multiplied by 100, involving in assuming steam to be an ideal gas, and the region where steam can be treated as ideal gas with less than 1% error. So this is when we have less than 1% of error, we can consider that steam is this is a steam is as ideal gas. Otherwise, here we cannot consider that the steam is an ideal gas. And this is the percentage of error at each point here. Okay, so this is the region of steam as considered as ideal gas. Like that, we finish our chapter. So summary: pure substance. We saw pure substance, phase of pure substance, phase change process of pure substance. We saw compressed liquid, saturated vapor, superheated vapor, saturation temperature and saturation pressure in the table. Property diagram for a phase change process. We saw TV, T versus specific volume diagram, P pressure versus specific volume diagram, PT diagram, pressure temperature diagram, and PVT surface. Property of table, we can get enthalpy from the table. We can get saturated liquid, saturated liquid vapor mixture, superheated vapor, compressed liquid phases. This is phases. Reference state and reference value. The ideal gas equation of state is water or vapor. Ideal gas, we saw that it depends on the pressure. At low pressure, we can say that it's ideal gas. So thank you for your attention. We finished like that chapter number 3. Don't forget that on Thursday you have a quiz. It will be about this chapter, and during the discussion session, I'm going to explain in more details what we can get in the quiz. Thank you very much for your attention.